Okay, let's take a look. We've got some graph here. Kind of looks like y equals x squared, maybe. I've broken my interval from 0 to 3 up into 6 sub-intervals. So we've got 1, 2, 3, 4, 5, 6 rectangles I'm going to use. In this particular piece, if we look at this one right here that goes from 2 to, what is that, 2.5, I'm using the left-hand endpoint to find the height of that rectangle. See, this rectangle uses the left-hand endpoints, and you can see that this approximation will underestimate the area. It's missing all these little white spaces here. Whereas using the same partition, this is still the interval from 2 to 2.5 right there. Now, if I use right-hand endpoints, so this rectangle here is built by finding the height at the right side and going backwards. Now I'm overestimating by all this amount. Now, if we take more and more rectangles, that's what these pictures are showing, notice the amount I'm missing by gets smaller and smaller. See, even if you zoom in here, see, this guy is an underestimate by this tiny little amount. The more intervals you take, the better your approximation gets. Okay, let's do an actual example here. And we're going to do this both ways. So we're going to do left hand and right hand. And you'll see we'll get two different answers. So I've got y equals x squared. And I'm going from 0 to 2 using 4 rectangles. So here will be 1, 2, 3, 4. I'm at 2. That's the point right there, by the way. 2, 4. X squared. Okay, so let's figure all these out. My delta x is always b minus a over n. That's how wide each of these will be. So that's 2 minus 0 over 4. I'm counting by a half, 0.5. So this will be 0.5, 1, 1.5, and 2. I'm going to build rectangles at each one of the left-hand endpoints. My area will be approximately the sum from I equals 1 to n f at xi times delta x. So right here, here's my first spot. The height there is 0. My first rectangle, I'm finding the height at 0. So this will be f at 0 times 0.5 plus this guy here, this rectangle. I'm using the left-hand side of this interval, f at 0.5 times 0.5 plus, now this guy, f at 1. That's the height right there, f of 1 times my width, 0.5. Just every rectangle, length times width, plus this rectangle, f at 1.5. Times my width, 0.5. Okay, I'm going to factor the 0.5 out and just add all those up. F at 0 is just 0. 1/2, remember, my function's x squared. When I say f, I mean I'm plugging into this function. That'll be 0.5 squared plus 1 squared plus 1.5 squared. And I factored that 0.5 out so I didn't have to keep multiplying by it. All right, let's throw that in a calculator. And just for completeness, all right, I mean, 0 squared is 0, but I'll put it there. Okay, so I want 0.5, and then I'm just going to put all this in parentheses. I'm not going to type the 0 squared. 0.5 squared. I shouldn't have to type the 1 squared. 5 squared. I get 1.75. So my left-hand sum is 1.75 square units. So if it depends on what our units are here. If this had units of meters and meters, then these would be meters squared. This is an area. And we can see literally from the picture that that's an underestimate because I didn't count that chunk, these little triangle kind of pieces. I missed all of those. This is an underestimate. Now, if we do the same approximation using right-hand sums, so now I still have the same partition, 0.5, 1, 1.5, and 2. Now in each little section, I'm going to use the right hand and I'm going to come backwards. So I'm going to go up right there and come backwards. There's my first rectangle. Here's my second rectangle. Go up to the graph and come backwards to fill in that rectangle. My picture is not very great here. So you can see this is an overestimate. I'm overestimating by all of this. And by the way, this amount that I'm under there is not going to be exactly equal to the amount I'm over here. Like they won't, I could not just average them and get it perfect. It would be pretty close though. Okay, so this is the sum, the area will be approximately equal to the sum from I equals 1 to 4 of f of xi plus 1. So in each interval, I'm using the I plus 1th x value times delta x. So in the first, this is I equals 0 here. This would be I equals 1 in the 0th interval. Okay, so that'll be 0.5 times f. Here, I'll do it in the same order I did it over here. So this guy right there, his height is f of 0.5. That's this height. His width is 0.5. This rectangle, his height is f of 1 times his width, 0.5, and so forth. This guy's height is f at 1.5 times 0.5, and then finally his height, f of 2 times 0.5. And again, I'm going to factor the 0.5 out. So that'll be f at 0.5 plus f of 1, f of 1.5 plus f of 2. Notice we get a pretty similar expression as to what we had before, only now instead of starting at the very left-hand side, that one's missing, and we added in the very right-hand side. A lot of repeats occur in both lists. This will be 0.5 times 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared. Again, why am I squaring? Because that's the function, x squared. All right, well, let's throw that in a calculator. Like, I'm just going to retype the whole thing, but it's pretty similar to what we just had. $3.75. I should put equals here. That does equal 3.75. Okay. If you're curious, like you would not need to know this yet, the actual answer, so this was the right-hand sum here. This is an overestimate. This one was an underestimate. The actual, the real answer is what we call the integral from 0 to 2 x squared dx. So I'm giving you a little foreshadowing here. You wouldn't know this yet. And now we integrate x squared. That would be x cubed over 3, evaluated from 0 to 2. This is what we call a definite integral. And now we plug in the top minus plug in the bottom. And that is 8/3. So 8/3 is about halfway between the overestimate and the underestimate. It's not going to be perfect. So let's average our two estimates together by adding them together and dividing by 2. And see, it's not perfect, but it's closer than either of those were. Now, later in Calculus 2, you're going to learn even better approximation techniques. One's called the trapezoid rule. One's called Simpson's rule. Like there are a bunch of, there's the midpoint rule. There are a bunch of different ways to build these Riemann sums. We're just learning the basics here, left-hand and right-hand sums. And again, in the real world, this is what we use. Okay, let's do the same thing using a picture here. So I'm going to approximate the area under this curve by using left-hand sums. So the area will be approximately equal to the function value at each left-hand point times my delta x. And then I want to add all those up. I equals 1, 2, 8. It says we're doing 8 of them. Okay, so my first one, my function value here is right there at 3. I want that area. That's my first rectangle I'm building. So this will be the height, 3 times my width is just 1. Plus, now I'm at this point. So that was number 1. Number 2, this region here. I'm using in this region, I'm looking at these x values. I'm going to use the left side as the height of my rectangle. And like literally, we could just count squares here. How many squares do I have? 1, 2. That'd be 2 times 1. That was number 2. And I'm just going to keep going like this. Here's my third one. I'm using the height on the left-hand side of this interval. So 1 times 1. 2. That's the height. My delta x here, let's write that out. Delta x equals 1. So 2 times 1. 3 times 1. So this was number, see, this was 3, this was 4. So 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah, I'm on my fifth one. Okay, I just wanted to make sure. Here's the sixth one. So I'm using the height at the left-hand side. So here's my sixth one. Plus, what do we got there? 5 times 1. Seventh one. Oh, did I lie? Yeah, sorry. That was 4 times 1 right there. 4 times 1. Here's my seventh one. Here's my rectangle way up here. 5 times 1. And then finally, this rectangle here. 4 times 1. Okay, so there was the seventh rectangle. There was the eighth. And that literally all we got to do is count all the rectangles I've shaded here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, I think. We'll pause and count that again. Yeah, it was 24. That was using left-hand sums. We could play the same game using right-hand sums. And you'll see that on right-hand sums, instead of, say, in this interval right here, instead of having an underestimate, we would have an overestimate because our rectangle, if we used right-hand sums, would look like this. Okay, so as I've been saying, we're building Riemann sums. That's how this is pronounced. A lot of times you'll hear people say this wrong. This is a German name. With German names, you pronounce the second letter. Think Einstein is EI, and you pronounce it I. Riemann is IE, and you pronounce it E. You're pronouncing that E there. Riemann sums. And a Riemann sum is a finite sum that when we take the limit as the number of intervals goes to infinity, which is the same thing as the limit of delta x goes to 0, we end up with the actual area. Okay, let's do another one. So we want a lower sum here. We don't know yet if we want to use left hand or right hand intervals. So let's graph this guy. He's 10 minus x squared. We know his graph looks like this. I want to go from 1 to 2. I just want this area right here. This is what I'm after. That actual area. Let's draw that guy, blow him up just in that region is all we really care about. So here's 1, here's 2, and I'm going to have some graph that's coming in like this. I'm going to break this up into 4 subintervals. So my delta x is always b minus a over n. That's a, that's b. So 2 minus 1 over 4, that's 1/2. I'm counting by 1/2 again. I'm counting by 1/4. I said it and it didn't make any sense. I'm counting by 1/4. So here's 1.25, 1.5, 1.75. Now let's take a look at one of these and see if a left-hand sum or a right-hand sum will give us an underestimate. So let's look at this guy right here. If I were to build a left-hand rectangle, it would look like this, using the left-hand side as the height. That would be an overestimate. Because see, look, I'm going above the graph right there. That right there would be extra that I don't want. If I want an underestimate, then building this rectangle using right-hand sums, going to the right side of this interval and going backwards. Right-hand sums will give me an underestimate or a lower sum. So we're going to do a right-hand sum. So each rectangle, so let's say the area of the ith rectangle will be the function value at the right-hand side times delta x. Then my total area will be approximately equal to the sum from I equals 1 to 4. That's how many rectangles I said I had. F at the right side times delta x. Okay, let's write all those out. So let's look at this interval here. That first rectangle will look like this. That will be F evaluated at the right side, 125, times delta x, which was a quarter, 0.25. This next one, right here. So I'm in this interval, the right side is 1.5. That height, literally this distance right here, is the function value at 1.5. Times 0.25. Remember, we're finding an area of a rectangle, the width, length times width. Plus the next one will be right here, f of 1.75 times 0.25. And then finally, this guy right here, f at 2 times 0.25. All right, now I got to actually go through the work of plugging all those into the function itself. So let's find all these separately. F of 1.25 will be 10 minus 1.25 squared. So forth. I'm going to write all these out, then I'll throw them in my calculator. This one we can do in our heads. F of 2 will be 10 minus 2 squared. That's 10 minus 4. That one will be 6. All right. I'm going to throw all these in the calculator. I'm going to pause. You don't have to watch me do that. Okay, so here are all the heights I got. And remember, each of those is multiplied by 0.25. So I factored the 0.25 out, type that all here in the calculator. What happened there? And got this answer. So 7.28125 is our approximate area, and that would be a lower bound. The actual area has to be bigger than that because we underestimated on each of our rectangles. Okay, I think that's a good place to stop here.